We need to imagine some kind of physical processes that have in computer. But main thing that we need to figure out is what is electricity, because mainly computer is electrical appliance. This is electrical device. So everything that happen inside and outside of the computer is electrical events. So before we go to the computer and computer applications, I would like us to understand what is the principles of electricity. And the first thing that we need to understand before we understand electricity is what is an electrical carrier. So the first thing I would like to mention the structure of the matter. If you go for structure of the matter, then the matter has nucleus, and around the nucleus you will find so-called orbital, and this device named atom. Can you see me, guys? Everything is okay?
Yes.
Yes. So atom. The kernel or nucleus of atom contain positively charged particles named protons. Protons. Protons has positive charge. You know that any charge has two signs, positive and negative. But atom must be neutral electrically, so everything around must be charged negatively. And negative particle that also appears as a cloud named electron. This electron is spinning around the nucleus or kernel with such a high velocity, so you cannot find it where it's now. You will see it as a cloud, only as a cloud. So, folks, this is a very simple atom named hydrogen. Hydrogen is a gas. It's a part of atmosphere. But atom could be very complicated. For example, if you go for nucleus that contain 8 protons and some neutrally charged elements named neutrons. So around this nucleus, you will find the orbit when you can find 8 electrons. And this element named oxygen. You know, folks, when we contain 2 atoms of hydrogen and 1 atom of oxygen, we'll have water. Water is what our bodies actually created with. We have 80% of water. Now, we know 3 aggregate states of matter because when atoms are very near to each other, like very high density material, very high density like this, they got to each other very close. So this is hard materials, hard body. When we're talking about atoms quite distance each other, that is liquid. And when the distance is quite far, that is gas. Okay, so the structure of hard things, of hard bodies, is very interesting. So most of them are metals. So you can find metals like copper, silver, gold, iron, and aluminum. And when you get a very um, powerful microscope, and when you go inside, you will see atoms of these materials connected to each other chemically, like this. I put 4 atoms connected to each other, but 4 others will be connected to each other, like this, and 4 others will be connected to each other. And I can continue, and you will see more of the structure, and the structure will go further and further and further. So atoms of the metal will be continue connecting to each other, and I will go and go and go. So you will see the structure will be long, long, long. Can you see it's go to the space? And this is nucleus of the atoms. But look at the space between them. Between atoms, we have kind of space where electrons can dance and fly. And you can see this illustration in my content one, in the very first topics. So electrons are inside. But you know that differently charged particles attract to each other. But when they charge similarly, they will be not attracting but will push away from each other. So how to make these electrons to attract to something? We need to connect to this piece of iron positively charged battery. Let's do this. So that will be, let's say, double A battery. I'll put it like this and put here AA, and negatively charged end I will connect to this end, and that is negative. Look what's happened. Electrons attracted to this plus will go and go and go near the plus. So that will be electrons concentrated to the positively charged end. Then they will go far from other end. So other end will be charged positively, and positive charge will be attracted with the negative pole of the battery. So what has happened if this contour is closed? That electrons will go through the battery because battery is conductor, and they will go through this conductor and then will be returned this uh, to this end, and then we will see permanent motion of the electrons because battery create electrical field electrical field. Now folks, I would like to tell you that the motion of electrons in metal or in liquid or even in gas named electrical current. Electrical current. So electrical current, folks, can manifest itself with different physical events. You know that electrical current can feed the stove, so that will be a temperature that is manifestation. Electrical current create a magnetic field, so the electromotor is spinning. So electrical current create magnetic fields. What else electrical current can do? It can create um, motion. So you can see that like electrical scooters and other devices, okay? Electrical current can feed the fan so it can move the air and many other usage. Folks, I would like to speak about electrical current that give you a light. Look at this. If I take the light bulb, you know the light bulb is the device that use tungsten filament and it could be fed from the electrical element such a battery. This is my device. And I'll say this is plus, this is minus, and that is AA battery. And this is small electric lamp that we use in flashlight. So you see this switch. Switch can break the contour or can make it. You know, we have such a switches on a wall. So that is a switch on a wall, right? When you go to the dark room, you turn the light on and then light is on. So what's happened if I close this switch? The light will be shining. When I break it, the light will be turned off. Now I would like to see manifestation with magnetic field. Folks, if this is the conductor, let's say electrical wire, and I will connect it to the battery. Again, I will put this battery minus plus, and I will connect it here, and this is straight conductor. The magnetic field will be around it like rings, and you can discover it if you put inside something like a metal, like a key. But this from the one where the magnetic field will be quite weak. To make it more powerful, we need to amplify it. To amplify it, we will go, say it again, amplify. We need to amplify it. For amplification, folks, I will use something like this. I will go for this point and then I will make a coil where each loop will be bringing the electrical field. And to amplify it, I will put inside piece of iron because iron has a feature for amplification of the magnetic field. You know the iron is magnetic material, such a kernel here, such a core. So when I connect this to the powerful accumulator, like the battery of my car, then magnetic field of this device will be quite powerful, quite powerful. How to measure this power? If you position here something made from iron, for example, that will be just a key made of iron, and I will do like this. This is a key. And when you make this contour closed, the key will jump from the table and will be attracted to this device. By the way, folks, this device named solenoid. Solenoid. Then when you cut the line like this, you will make a breaker and you will break the wire. You will make a breaker and break the wire. When you break the wire, the key will fall down on the table because nothing will attract it anymore. So folks, can I use these two devices, the lamp counter and the magnetic counter here, to answer the question? If the question has only one answer, yes and no, I will tell you this answer is yes. I can use it. Folks, take a look. Um, when somebody asks me, can I be your guest? And I will tell, today I will be busy, but tomorrow you can. I'm not sure that tomorrow you can, but I'll let you know. How somebody let you know that he is willing to receive you as a guest? So he can have this lamp. So if you actually invite it, the lamp will be on. If you reject it, the lamp will be off. So the same thing here. When the counter is on and iron detail like a key attracted to the solenoid, then you can see it with your eyes and then you can say go. When the key is on its table and it's not attracted to solenoid, then you can say stop. The same is here. Light is on, go. Light is off, stop. Folks, in the computer, these two things is very, very important because people use this kind of conditions. But you can see here and here, these two devices, they have two conditions. So the people who invented this named it binary devices. Binary. Why it's binary? Because binary meaning two states, two conditions. Okay, but people design it a little bit later. So far, I would like to tell you folks how people start using connectivity and magnetism for telecommunication. I need to change my piece of paper and then you will see it. Folks, telecommunication was a dream of people for a long time historically. People wanted to communicate with each other remotely, distantly. And there was one man in 1830s, actually in 1833. He was a genius, very smart man. His name was Samuel Morse. Samuel Morse. This Samuel Morse actually made different research with solenoids and literally find out that we can make solenoid like on this page. On the page I draw like this one. I'll show you again. This solenoid can attract the key and can fail the key down. So he made the same device, but he made it differently. He put the switch in one city and then battery somewhere in the middle, plus minus. And then he put the long wires through the whole region. Let's say this is Brooklyn, this is Bronx, here, here, and he put the key visible for operator in Bronx. Now look what's happened. The operator in Brooklyn can push down the switch, and then electrical pulse will go through the wires and attract this key to the solenoid. Create a knock like this. Then when operator release the switch, the key will go down. So operator can make the short push for the switch. Then you will see such a short pulse, just a short knock. And then it could be a long push. And then Morse created the alphabet, which actually can use short push, which was named dot, and long push, which named dash. Combination of dots and dashes create Morse alphabet. Folks, dot and dash, letter A, two dots, one dash, letter B. I don't remember all of this, but you can find it, Google it and find it on the internet. But I remember that three dots, it's letter S, three dashes, letter O, letter P, this is three dots and one dash, this is P. This is what I remember. So transmission to this kind of communication device looks like this, like knocks. And operator named telegraphist. Telegraphist. Why telegraphist? Because this device named telegraph. Telegraphist can see these knocks and actually can hear it and can write down the message that came from the transmission to his reception end. But folks, this is only one direction of communication named simplex. But nothing actually disturbing us to make this opposite. So I will make switch in Bronx. I'll put battery right here, plus minus. And then I will make the long wires and make solenoid in Brooklyn. I will make solenoid in Brooklyn and put key here. And operators here will see when key is attracted, when key is fell. So the same code table could be realized here on this end and on this end. Folks, this is nothing but the code. Please remember this word. This is very important word in computer science. Code. What is code? I can give you definition, but you will find definition in content one recording in Blackboard. Folks, when we thinking, let's imagine, we're thinking. When you think the different items could be imagined in our brain. For example, I have a pen in my hand. So the pen. But when I tell you pen, you can imagine the pen. When I'm talking about tweezer, this is tweezer, right? You can see it, metal tweezer. But when I say tweezer, you will be able to imagine tweezer. This is remote control. Look at this. Remote control. So when I said remote control, you can imagine remote control. And this is a phone, right? Look at this. This is a phone. So folks, different images actually could be in our memory. But listen, when I tell you about these items, like I tell you telephone or remote control, you are not seeing them. I'm not demonstrated them to you. I just pronounce their names. But folks, names is just sound. So in my brain, I have a substitute table, which actually allows me to substitute the image of the device or image of the item with the sound of words that actually substitute this image. Now, my transmitter is my articulated mouth, which actually can pronounce different words and pronounce sounds. So you have reception end, and in this end you have receivers, and this receiver is your ears. And when you hear the sound, the object that I'm speaking about is reflecting in your brain. So that is different process from the code, which is words that you receive in your ears, that will be converted to kind of visible objects. You can see them in your memory. So folks, code is something that substitute real names. So for example, I can say letter A in the code, that will be tata. Letter B, I said B, but in the code will be dot dot dash. Save our souls signal. Signal Mayday when something getting down, droning, falling down as a aircraft. It sounds like this. And this is code. Folks, this is code. So if you remember or you can write it down, I can dictate. Code is the material object that substitute the real item that we're talking about or naming. Folks, every language has its own code, meaning this is dictionary. The code table of any language, it is dictionary or vocabulary. When I switch my vocabulary to the different language, you will not understand what I'm talking about. For example, listen carefully. Привет, ребята! Я бы хотел вам прочесть все мои лекции за 1 час. I bet you do not understand what I'm talking about, but I'll tell you guys that this is Russian language. I can switch code table to Hebrew and said Shalom Manishma. So every time that we coding, and the coding when I speak, this is already encoding, I need to have code table which actually shows me the correspondence between real names and encoded names. This is code table, and I have to have it identical on the transmission and on reception end. Folks, Samuel Morse became a very wealthy man. He works on this telegraph with his with different banks, help them to play on the stock market and so on. But I will tell you that Morse table is very convenient. It is very cheap and simple apparatus. But this is one disadvantage. When somebody transmits secret information from one end to other end, the operator that sitting here can actually know what transmission telegraphist actually talking about. So two people already know what it's about. It's not secret, it's not secure. When you send and receive email from your friend, you're quite secure. But this is not secure communication. This is disadvantage of this communication system. But folks, another disadvantage that we have two positions of the switch. Switch has two positions. What is position? On and off. But this is three code elements. What three code elements? This is dot, dash, and space. space between dots and dash. So this is not totally 100% convenient. And then people tried to make a different telegraph that will work without telegraphist, uh, only from keyboard. And this telegraph must use only two elements in encoding, on and off. And such a man was in England, in Great Britain, uh, and in France. His name was Badeau. Badeau. Badeau says, can we define on as 1 and off as 0? The same as true as 1 and false as 0. People who actually was introduced to this kind of mathematics, but this is binary mathematics, they ask me why 0 is off, why 0 is false. Folks, that is very simple to explain. If I tell you that I gave you $5 and that is false, that will be multiplied by 0. So you'll get 0 if this is false. If I tell you you get $5 multiplied by 1 and this is true, you will get $5. Truly. Okay, now, people who designed it, they named binary devices that have only two positions, like this. They name the information that they bring 1 bit. 1 bit is one binary digit. Binary digit is only 0 or 1. Why this is only 0 or 1? Because in binary system, there is no other events than open and close, like on and off, true and false, left and right. Folks, you can find a lot of binary devices. For example, the door lock could be only in two positions. The door is locked, you cannot come in, and the door is open. Then there are a lot of non-binary devices, folks. For example, steering wheel in the car. This is not binary because it has whatever multiple positions. But brake pedal is not binary because you can push a little bit, but you can push with all your power of your leg. But what is binary? Binary is head and backlight. Okay? So 1 bit is 0 or 1. So folks, number of combinations in 1 bit is 2. Number of combinations is 2. That's interesting because if I say I will put 2 bits, meaning 2 lamps, take a look, 2 little lamps. Every lamp will have a switch. I will assign 0 as off and 1 as on. Now take a look. Both lamps are off. One is on, another is off. This is on, another is off. And both on. How many variations here? 4. For 2 bit, we have 4 variations. For 1 bit, we have 2 variations. Now my question is, how can we see number of variations for 3 bit? Let's say I have 3 circles. When circle is empty, I will say this is 0. When the circle is black, I will say this is on or this is 1. So 3 bit. And I will go for this 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Interesting. How many total? 1, 2, 3, 4, 5, 6, 7, 8. 8 variations. Why do we need to calculate number of variations? Folks, because people would like to move not only 2 wires, but instead of 2 wires, they will be able to use number of wires to transmit alphabetical symbols. But how many alphabetical symbols we have? Somebody said 26, but 26 is just small symbols. To have more symbols, we need to have capital letters. That is another 26. Then numbers 0 to 9. Then punctuation, dot, comma, semicolon, colon, and so on and so on. Then mathematical symbols like plus, minus, divide, multiply, and many others. Folks, the set of characters in English language, when you can see it on keyboard, is 256 different symbols. 256 different symbols. But look what happened. For two variations, for one bit, we can encode only one set of letters, like letter A and letter B. When I say letter A will be 0, letter B will be 1. But when I take 2 bits, I can encode more. Look at this. That will be A, B, C, and D. How they look like? A 00, B 01, C 10, and D 11. Folks, question. What is dependability, mathematical dependability? Number of variations from number of bit. Let me tell you. Number of variations, Q, quantity of variations, is equal to in the power of n. That is framed formula, where n is equal number of bit. This formula will be on exams. Please do not forget. Okay, now let me change the piece of paper and you will be able to listen me further. Alright, so we already know that 3-bit can give us 8 variations. 8 variations could be assigned 8-bit. 3-bit or 8 characters. 000 for A, 001 for B, 010 for C, 011 for D, 100 for E, A, B, C, D, E, 101 A, B, C, D, E, F, 110 that will be G, and 111 will be H. Look at this. This is letters, alphabetical letters, and this is corresponding code. The binary code that we can use to substitute this letter when we have transmission lines multiplied by 3. Not one transmission line, but 3 transmission lines. But in 3 transmission lines, we can only submit 8 symbols or 8 letters. Definitely if I say 4-bit, 4-bit will give me 16 variations. 16 variations. Folks, how that could be? I will go for this. 0000, 0001, 0010, 0011, 0000, 0100, 0101, 0110, 0111, 1000, 1001, 1010, 1011, 1100, 111, no, 01, 1110, and 1111. Oof, I was tired to list them. But look at this. Every single line of this code could be used for one symbol of alphabetical set. So that will be A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. But I cannot use more because that is not enough codes. Why 4-bit gives me 16? Definitely Q for 16 will be 2 in the power of 4, which is 16. So folks, it's obvious that I need more wires or more bit to transmit the entire set of English language symbols. If I take 5 bit, I will have 32 variations. If for 6 bit, that will be 64 variations. For 7 bit, that will be 128 variations. Take a look, folks. For 1 bit more, the quantity of variations doubled. We started with 2, multiplied by 2 will be 4, multiplied by 2 will be 8, multiplied by 2 will be 16, multiplied by 2 will be 32, multiplied by 2 will be 64, times 2 will be 128, and eventually 8 bit create 256 variations. 256 variations. Folks, that table, which actually include all English language letters, punctuation, numbers, and everything else, must have 8 placeholders, and I will put them right now on my figure. 8 placeholders, like this little table. Each placeholder could be 0 or 1. Number of non-repeating variations for this placeholder will be 256. Number of bit is 8 bit. 1, 2, 3, 4, 5, 6, 7, 8. Number of variations Q 256. So folks, when people consider that this kind of construction, this kind of idea can cover the entire alphabet for American transmission, they make this standard. And they call it American Standard Code for Informational Interchange. ASCII. It's read like ASCII. ASCII code table. So what you need to do when you come home, you need to Google ASCII code table, which actually correspond 8 bit to the letter. For example, 10010001 will be A. 10010010 will be B, and so on. Please print it and have it in your possession. ASCII code table. Need to remember that will be on exams. ASCII code table. But folks, combination of 8 bit also has a name. This combination of 8 bit named byte. And bit and byte are unit for information. So if I say the word mommy, how many letters here? 1, 2, 3, 4, 5. What measurement of information I can say this word bring to the world? I can say the 5 letters, this is 5 bytes, or each byte is 8 bit, so 5 multiplied by 8 will be 40 bit. 40 bit is cost to pronounce the word mommy, informational cost. Why I say cost, folks? Because transmission, reception, and saving, storing of information is costly. It costs some money. When you get your memory, when you get your flash drive, you need to pay for that. More capacity for this device, more money you pay. So you need to measure how much information you actually can store or send or receive from the device. Okay, so we have now ASCII code, and you need to remember that ASCII code table contain 8 bit for one character. Number of variations or number of characters that this code table can represent is 256. But folks, 256 sometimes is not enough. I can tell you that there are many languages on the planet Earth. There's a language that I can show you like this way. What is the language? Chinese. The different is Japanese. The different is Cantonese. The different is Hebrew. Hebrew has something like this. Ethiopian language. Russian language, folks, in Russian language, we have letters like this, letter U or letter Y, and letter H, English language, this is letter N, but letter H looks like this in Russian language. So a lot of languages, folks, the tons of languages, every language has, even Korean, I forgot, Korea, Arabic language. Folks, I don't know Arabic language. Al Quran is holy book that actually use this language. So how to encode Al Quran or how to encode Torah? You know, Torah is Jewish Bible that actually use Jewish alphabet for that. Hebrew. We cannot be in a frame of 8-bit per character because it's only 256 letters. So people who designed computers, they said, let's use 2 bytes, 1 byte and another byte as a basic for encoding. And one of the 8-bit and another one is 8-bit. Total number of bit will be 16. According to my formula, like this one, Q is equal to in the power of n. For 16-bit, that will be Q 2 in the power of 16, which is, I don't remember exactly, but that will be 65,532, something like this, approximately. Approximately 65,000. You can take calculator and make it exactly what it gives you. So folks, if you use encoding table with 16-bit per character, you will have more than 65,000 placeholders for any letters that planet Earth can use. And this code is quite contemporary code. This code named Universal Code or Unicode. Unicode. And this is not a secret that Internet actually has this code as this basic because Internet is international network. That's it, folks. Thank you for coming. This is exactly time to finish this lecture. Now it is time to ask me questions. No questions? So everything is clear. I'm glad to hear it. So, folks, um, I will announce our meeting again. Which announcement, and then you will know when we see each other again. So far for the class SiS101 we will still meet each other online in quite the same time that we must use for the meeting in class. That is much better, much more convenient. Thank you for being with me. Again, if this is no questions, I can wish you good luck and close the session.